Thank you. So this afternoon, I will try to share some of our experiences in combining together Internet of Things and machine learning techniques. Does the microphone work correctly? Okay. And my name is Stefano Terna. I'm the technical co-founder of TomorrowData. TomorrowData is a small and young startup operating in the domain of bringing IoT and machine learning to small and medium enterprises. We are committed in sharing our results with open source, and I already invite you to attend to another talk that we will take on Sunday at 3 about the IoT project, which is an IoT enabling platform made open source on GitHub. The technologies with which we operate can be summarized in trying to put the ideas of continuous integration into the Internet of Things, and what is more tied to the present talk, a concept of remote machine learning. So when we try to put together machine learning and Internet of Things, usually we can see them bound in this way. Machine learning is bound to the internet side of the Internet of Things. We just treat remote devices as we can treat users of a website generating logs or transactions generating records on some database, and then we collect a huge amount of data and we need to do some kind of with this to extract useful and novel information from this data set. Don't know. Okay, already at this point we can stress the fact that collecting a click of a user from a website is not the same as collecting events from a remote device. Just to anticipate something of the example, if you connect an accelerometer to this device and these accelerometers capture acceleration at a frequency of 800 Hz, you have 800 events per second, and you have to decide if you want to collect them on a cloud database, or you have to do some pre-processing in order to. So it is not the same as big data. Somebody say that big data are not enough for the Internet of Things big data. Actual big data are not enough. Hadoop doesn't apply just straight as you could imagine. But what about if we start thinking about this kind of connection? So applying the machine learning to the things side of the Internet of Things, and you can imagine what can happen. We try to put the intelligence, the adaptive behavior on the remote things, and this is why we try to call it remote machine learning. This is the main topic of this talk, and we will try to describe what can happen binding machine learning with the things side of the Internet of Things, using a real-world example with which we dealt with one of our customers. And throughout the layout of the presentation, we will have a description of a quick description of the industrial case of the domain, a high-level description of the solution, something that arises when you have to design edge IoT devices. So we have some constraints, and these constraints generate some further constraints on the machine learning pipeline we have to manage. So we try to define a sort of IoT machine learning pipeline, or maybe we ask for the need that the community start working defining such a kind of new sort of pipeline. And as usual, a machine learning pipeline should have these subcases, so you have to annotate raw data. We speak about supervised machine learning, namely neural networks, so this is the context. So you need to annotate raw data, but we have some differences in annotating raw data, which is just keeping a list of images and asking people to label them, because they can do it whenever they want. You can stop, pause the work, and restart it after. While if you work with Internet of Things, often you have to do labeling in real time, and this can arise some issues. we have a usual pre-processing and training, and we will need to see the consequences of applying these kind of things in the Internet of Things scenario. So for the domain, quickly, a lifeline, which is the title of the talk. A lifeline is basically a cable, a stainless steel cable, installed on top of roofings, and workers attached to this cable to work safely in the hive. So this is, I mean, not a smart thing, it's a dumb thing. What kind of issues this kind of system present? Presence detection issues and maintenance frequency issues. Why presence detection? Because the worker operates in unsupervised areas, meaning that he records his presence at the main entrance, but after that, in normal situation, we don't know where the worker is. And this lack of knowledge about his real presence may delay the expected contingency plan in case of an accident. So this is an important safety problem. Moving to the other side of maintenance frequency issue, cables need maintenance to preserve their functionalities. But it is very different if a cable is used for 10 hours per month or 100 hours per month or other, because it exhibits different degrees of wear, of consumption. So the lack of knowledge about the real usage forces the maintainer to operate basically starting from repetitive regulations, which can turn out in either too early interventions, which are economically non-optimal, or too late intervention, which even worse are safety non-optimal. So this is the scenario, and in this scenario, these two issues could be tackled if we had an automatic detection, presence detection system of the worker on the lifeline. So this is the settlement of the problem. Because of course, if we know where the worker is attached amongst different lifelines, we can direct straightly the rescue intervention, and if we know how much it has been attached to the lifeline, we can compute the consumption of the cable itself. Current attempts to track worker presence rely mostly on voluntary action of the worker. So if the worker doesn't comply with the required policies, use a badge or push a button on an application, or even worse, signing a logbook, we simply miss the information. So for the requirements, the first requirement for the system is that it should be automatic. It should not rely on voluntary action of the worker. It should be non-invasive, since the lifeline, the cable, should undergo strict regulations on how it is built, and we cannot modify it. We cannot modify its construction processes, so to introduce some kind of internal modification of sensors or things like that. And the last one is that it should be adaptive, so the same kind of lifeline and the same kind of detection system should work in very different scenarios where the lifeline can be installed, roofings or pipelines or things like that. For the idea is when the worker is attached to the cable by means of a carabiner. A carabiner is like a shuttle running on the cable, like when you go to the adventure park in the mountains. And this carabiner generates high-frequency vibrations on the cable. These high-frequency vibrations propagates along the lifeline, and we can collect them by means of an accelerometer on one of the two ends of the lifeline. So this is the main idea behind how to detect the presence detection. So how can machine learning and IoT help at this point? Because of course, just recording the acceleration of the cable isn't enough. A lot of things can generate acceleration of the cable on the roofings, not only the presence of a man walking on it. So we have the accelerations. This is the first introduction of the high-level solution. We have an accelerometer coupled to the lifeline, which capture the accelerations. The accelerations are read by a board installed near the cable on the roofing, and this is why we are speaking about IoT constraints, because we are not transmitting the whole bunch of accelerations to a remote server, we are just analyzing them on the field. The board reads the data, and then it processes the acceleration raw data by means of some pre-processing. We will go deep inside in a minute, and by means of a previously trained neural networks installed on the board. The objective of the neural network is to extract the human presence from the signal of the carabiner on the lifeline. The next step is more an IoT pure step, because we just collect the event generated, the presence detected event generated from the board, and we transmit it to an IoT enabling platform, which is the topic of the talk of Sunday. And at this point, operators on remote operating desks can have a lot of information available, so to know where the operator is working, or how much the cable has been used, and how to program future maintenance intervention. But this is just a user interface. Okay. As I said, we have to install the board near the cable in close proximity, and we have some constraints. The first one is that we have to power it with solar power. We do not have current on roofings. The second one is that we lack wired connectivity. We do not have broadband connectivity there. Or if it is broadband as 4G, it is a very high cost, so we cannot just use it to transmit all the data somewhere. As when you start speaking at the phone and the data are transmitted, interpreted, and put it back with conversion in characters. These are just very small data compared to this one. And the last, another constraint is a power consumption one, since we have solar power and batteries and some consumption of the CPU and some requirements from the customer that wanted the system stay up for 5 days in case of total absence of power energy coming in. An extreme case, but anyway, it's an engineering limit. We must fulfill strict energy consumption constraints. And the last thing is that the neural network must fit into the board. Sorry. Okay, so how can we achieve this sort of training that we described, giving it for granted, but now we go into much more depth. Raw data are annotated to generate training and test set as usual. The artificial neural network is trained to extract the worker presence from the raw data. And then, and this is a very Internet of Things machine learning binding, then the neural network is uploaded back to the device. So there are two phases. One in which you can prepare the algorithm offline, and say you have a factory default of algorithm for your boards. And then there is another case when you find something new that you didn't know at training time, and so you need to perform a new training and then send the algorithm back to the board. And so you need some mechanisms of firmware upgrade of the board. Okay, this is where Python and stacks comes into help, and how we built the entire platform to do this kind of things. So the pipeline is like this. These are the remote devices, and for whom of you knows about this kind of processors, Cortex M0 and M4 are quite powerful processor for the consumption they exhibit, but they are not comparable at all with something like the processor of a modern smartphone. So the device produces data, which are in a training phase transmitted remotely. So we do not transmit forever because they are too much, but we transmit windows of data, or raw data, remotely to the labeling and annotating interface. The annotating interface is built on top of Tornado, Blaze, and Bokeh. And this kind of stack helped us a lot because we, in let's say one case of 1 month of acquisition, resulted in 50 gigabytes of data. And then the annotator, the man who does the annotations, or I mean, at least the man who check that the annotations are correct, should browse these 50 gigabytes of data. And the Blaze server permits us to stream these 50 gigabytes of HDF5 data format, to stream it in JSON format in Windows to the Bokeh server, and the Bokeh server in turn to the interface. Then another part of the stack is that at the time when we started doing experiments for this problem, we decided to use R to do the training, specifically the NNet library of R. So we are out of Python. Apologies for that. And we need to transmit data back and forth from the Blaze server to R, and we use a PyRserve. But with PyRserve exhibit two kind of issues. The first one is that it is not parallelizable easily. I mean, you cannot just make processes we use multi-core inside of R. The second one is that if you use PyRserve on top of R, this is even worse because multiple sessions of R start messing up with data due to PyRserve problems. And the solution was to sandbox each instance of PyRserve and R into a Docker container, and using again DockerPy to orchestrate this container, and using, it is not written, Redis to merge the data on different instances. Of course, this can be done because we run different, multiple contemporary training of the same algorithm, and then use a winner algorithm to choose the better. Okay. And of course, as I said, how can we achieve the adapting behavior of the system? We train different algorithms for different cases. Starting, this is important always from the same case, and then adapting it, because the main thing that differentiates this case in this specific domain is the absence of man, not the presence. The presence generates almost always the same signal. What is different is the absence of the man that in different scenarios exhibit different kind of signal. For the annotation, we built a real laboratory of 140 meters long, and some particularities about the domain. I mean, this is a cable installed, and these are points of contact of the cable with the ground or with the roofing. And we developed an app to perform the real-time annotation. So for the real-time annotation, this is the point, as I said before, as I anticipated before. You have two kinds of problems. The first one is that you cannot use a message straightly from the application to the board, since the latency would affect in a random way the position of the markers. If you send a message now and then you send a message in 2 minutes, the latencies can be different and the marking time can be different. So you have to mark separately, independently, the two events on the two systems, and then find a way to synchronize them. And this is annotation time sync. So this is what we did. We basically hit with shots on the cable, and at the same time market the event on the application. This is the result of the acceleration of the shots, 5 shots given on the cable. You can see 6G of acceleration, which is a huge amount of acceleration, of course, because you're giving a shot on the cable. And these triangles are the contemporary marking time on the application. And you can see some offset, of course. Then you have to merge, to shift these red triangles in order to have your offset computed. We can compute this marker by means of some clustering algorithm. In this case, we use a k-mean clustering algorithm to detect the time interval where the most important kind of signal concentrate. And of course, these are the same traits of the k-means algorithm. And at this point, you can compute an average offset with a series of discarding outliers and things like that. So the green triangles are the shifted points marked on the application, and this is the offset, and this is the error computed in milliseconds, which is an acceptable error for our situation. The second kind of problem that can arise is that, okay, now we have shifted the marking on the application, the labeling, and so we have the raw data, and these are the real labeling of the data we did real time. But doing it real time proves the fact that you can do mistakes, and you cannot just say to the person who is working to collect data, stop working, because he do whatever he wants. You are in charge of labeling the data, he is not. So you can make mistakes, and so you need some kind of interface to detect and browse through the data to detect which are good, which are not good, and to discard eventually bad labeled data. For example, here you can see that this is a good annotation taken at 100 meters far from the accelerometer signal. Okay. And okay, just to recap, this is a high-level description of our data set. We worked a lot, and we collected walking, heating, corner traversal, silence, which is easy because you just feed it recording, but we collected silence on different situations, so suffers on concrete, on metal, or outside factors like rain, wind, or turbulence function in the morning and in the dawn. And okay, so now for the preprocessing. We collect 3 measures at 800 Hz per second, and we have to feed them in some way into the neural network. What we need, what we ended up with is a preprocessing which compresses the data from 2,400 measures per second to 150 features per second, because, as you remember, you have IoT constraints. Basically, what the preprocessing does is managing some physics, extracting the gravity from the acceleration. Then it manages time, performing statistical aggregation over time window. Again, we cannot install a recurrent neural network or such kind of constrained hardware, so we have to deal with time context in another way. And after the statistical aggregation happened, we can extract candidate features for the algorithm. Now, some technical insight about what can happen if you have to develop an algorithm on a constrained processor, which is one of the lessons in merging IoT and machine learning. Let's say you have to compute the standard deviation of a time window of your signal. So the first one is the usual definition. But it turns out that the second definition, which is algebraic precisely equivalent, is much more efficient from a computing point of view, because you don't have to recompute this quantity again at every new value of x which comes in, but you can just accumulate, you can just compute 2 accumulators, we call them, a square accumulator and a linear one, upgrade them at every new point that comes in, and then subtracting the value and extracting the result. But what happens if you ask some experimental physics? If you ask some experimental physicist, he will tell you that this second algorithm suffers from a problem known as catastrophic cancellation, numerical computation problem. The catastrophic cancellation is due to the fact that in the original algorithm you are subtracting small numbers because the value of x is very near to the value of the average of x in a small time window, and so the difference is small, and the sum of small number doesn't make you lose the floating point precision. While in the second case we first sum square number, so we obtain big numbers because they are positive, and then we subtract them, moving the operation at the high level of the floating point precision, and so losing precision. So, in an academic settlement, you just discard the second algorithm and say, well, you have to do the first one. But what about if you have some time, budget, and real case constraints that you have to deal with? Well, you have to find out an algorithm to check if the error generated by the catastrophic cancellation is anyway acceptable in your domain. This is, I mean, not particularly tied to what we did, so it is generalized, and we like to share this fact, which is known in experimental physics, but maybe not so in IoT or machine learning. So what you do, what you have is that you know the error, the nominal error of your sensor. In this case, we have an accelerometer, and on the sheet of the accelerometer, the error is declared. In this case, is 200 millig. So you can sample, draw from a Gaussian distribution a sample with the sigma of the Gaussian as the error of the sensor. Then what you have to do is to compute the difference. That you have to propagate the data inside here, so you compute the difference between the usual formula and the efficient one. Then you have to propagate the error within the first one and compute the error on the sigma estimate. And if the delta between the two algorithms is less than the error estimated on the usual formula, then your efficient algorithm is okay. Fortunately, what turned out is, for one of the cases, but for all of them, but you can just see here one of them. These are the numbers. This is the estimate of the error on the standard algorithm of the standard deviation, which is this one in our case. This is the significant digit on these numbers, so 6 is the last significant digit. And this is the distribution of the difference of the result of the usual and the efficient algorithm with respect to the exponent. So here is where exponent is 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. And you can see that since you have error on the 6th digit, and here you have a distribution concentrated below the 6th digit, you can just accept the result. The lesson learned from this example is that if you want to work with constrained algorithm and you have to come to compromise with what you are doing, you have to check. Techniques to check are available, and Python can help, because all this kind of computation done with NumPy on IPython are much efficient and very ready to be performed. Okay. Now for the IoT machine learning pipeline, we described the annotation tasks, we described the pre-processing. Now to the last part, the feature design and the training of the algorithm. Okay, so there are two, I mean, you can manually design your features, or you can let your algorithm extract the feature by itself. In this case, we extracted the feature, we designed the feature manually, and there are two reasons. One is because we wanted to gain insights on the domain problem was going on. The other one is, again, an IoT constraint lesson we have learned and we will see in a minute. So to describe one of the selection processes for the input feature to the neural network, this is one of the point we had to manage. You have two boundary scenarios in this domain. You have low accelerations when the movements happens at great distance from the accelerometer, and of course you have high accelerations when the movement happens at small distance. It turns out that these two boundary scenarios get confused easily from the algorithm in the testing case. So let's see what happens. This is a real data set. Here is the average of the acceleration on the z-axis, and I mean on the norm of the z-axis, because otherwise it should be almost zero. And this is the standard deviation of the same kind of quantity in case of worker presence and in case of no worker presence. So what you can say here is that these two kind of features can detect quite well a small area of all your domain. And you can see that the two boundaries we described before are not distinguished in any way. Of course, we are just using two features, so it's difficult to ask a neural network to do such kind of task, but we are doing step-by-step selection of features here. What it turns out is that if you add standard deviation over average, the idea, knowing the domain is quite easy to understand, because dividing the standard deviation by the average of the acceleration means that you are taking the noise of the signal and you are normalizing it, whether it happened at a high distance from the accelerometer or at a small distance from the accelerometer. And what it turns out is that, again, this new set of features is not able to distinguish the old cases, but it behaves a much better behavior. Of course, I said to you that at the end of the process, the features were 170, so not 3 like in this example. Anyway, just in this case, we obtained a good precision in detection. So, what happens in a neural network is that at this level, just a linear combination of input feature happens. The nonlinearity, which in this case is a sigmoid, happens here. Then here is where the algorithm learns how to fit the boundaries of your data. Sorry. And you know, we know nowadays that with deep learning, so adding new layers, intermediate layers, just do this fact, because this intermediate level automatically detects the need of adding a kind of feature like this, and it fed it into the next layer, and so the boundary is distinguished in this way. But the problem is that this kind of algorithm does not fit into the board we have to develop it into. And so we had to manually develop the feature so that a single layer feed-forward neural network could detect properly the data. And these are some recap results. So, of course, we stayed conservative on the false positive, because in this domain we didn't want our user to be alerted in a false scenario. We prefer to stay on the false negative scenario, and effectively counting occurrences over 10 seconds and putting a threshold as a post-processing on these kind of results gave us a detection precision of almost 100% of the cases. Thank you. That's all.
So, any questions? the speaker.
Hello, thank you for the info. It seems that the annotation of the dataset for the input to the training set of the neural network is very expensive because you manually have to label more or less each time an operator is working, right?
Yes, that's it.
So,
Expensive.
yeah, expensive, that takes time.
1 week of data collection.
Yeah, exactly. So you have to do this process every time for every lifeline, or you can extend the neural network to other...
Yes, you can. It turned out you can, because you have to do it the first time for the positive cases, which are hard to collect. Then what you missed in that collection are the negative cases, which are different in different scenarios. Because the neural network is very good at extracting the known scenario from a new negative one, separating from a new negative one. So what you can do is just to record the negative cases, in which in this situation you just let it recording data for 2 days or something like that.
Thank you.
You're welcome.
Hello. I just wanted to know if you can give us an hint of what are the other features you didn't show us. So besides the average and the derivation of the acceleration you collect, you said that you actually use 173 features or so. So can you give us an hint of what they are?
Yes, as usual in this situation. Thank you for the question. And let me see if I can go. Okay. Just a second for Google to help us. Okay, I have to go back to the preprocessing in order to answer to your question. Namely, what we had to do was, I briefly explained it before, but we have the sampling at 800 Hz, then the preprocessing is built on 2 sub-blocks. The first one, the middle one, is a high-frequency preprocessing where we just perform some high-pass and low-pass filtering on the signal, and we perform physical rotations to tackle with this problem that the sensor can be installed in random situations, or when the cable exhibits some degree of consumption, it starts sloping down, and so the position of the z-axis changes, and we have to re-rotate it back along gravity. And then there is another step which performs statistical aggregation over this high-frequency preprocessing at 1 Hz, so very slow in this scenario. These are the way we extracted this is the acceleration measured from the accelerometer. This is the acceleration of the cable itself, and this is the acceleration of gravity plus the factory offset of and these are formulas on how to extract them. Then we had to, okay, this is a high frequency preparation of the features. So you have the norm of the acceleration, you have the norm of the acceleration on y and z, and the norm of acceleration on the x-axis. Then you have this is an amusing function, because this is the logarithmic derivative of the signal, of the norm squared. This counts how many points are up and how many points are down. This is very useful when you have to train an algorithm on a signal, because you have to know, you have 100 points, and you have a window of 30 points all up. This algorithm can count these 30 points up when they are near to each other. So if you fed it into the neural network, you're giving a very important nonlinear information. You have, okay, derivatives of the signal were very important because derivative is the first expansion in the Fourier expansion of the signal, and the Fourier expansion served us to separate cases like a thermal expansion other situation. Okay, that given, what we did was to aggregate these outputs of the look at this as a huge vector at 800 Hz frequency of computation. And what we did was to compute aggregation over 800 samples and 4 times 800 samples, so a window of 1 second and a window of 4 seconds. And 4 seconds is the time domain of our problem. In any way you have to train some kind of algorithm on a time series. You always introduce a time cutoff. You have to introduce some sort of time correlation damping factor. Also, if you use a recurrent neural network, you must define at some point what is the damping factor when an older or a future signal become useless to the interpretation of the data. And this, in this case, is 4 seconds. And these are, finally, the answer to your question. So average, standard deviation over average, interquartile range. Again, interquartile range over average for the same reason I said before, kurtosis, skewness, and correlation. And why they are so much? Because any of this is computed on these high frequency indicators, and then any of this is computed on each of the 4 seconds and on the full interval. So.
Amazing. How much did it take to figure out this approach for this kind of problem? You did yourself, I mean it's, you discovered this, right? Or did you use something that was...
Deep learning is faster at detecting features than us. You can
of course,
no, let's say it took more or less 1 month of analysis. So not so much.
And there was no literature about it.
Not so much, but we had the help of not domain expert in the sense of lifeline, but physicists.
Yeah, I'm giving back. No, just the last little thing. Did you go directly with a neural network approach, or did you try a more linear or simpler approach before, like, I don't know, threshold over signal, integral, and counting experiments, something like that?
No, not simpler, maybe one more complicated, which is reservoir computation, which is kind of simulating a liquid which oscillates and learn and have memory of the signal that is passing inside it. And basically it is a non-trained neural network. You can just throw the weights randomly and stay with them, which is much more efficient, but didn't exhibit. But there is a lot of literature about reservoir computation. This is the only one we tested.
Hi, nice to meet you. May I ask you, how do you manage the age of the thing? I mean, I guess a brand new lifeline has a different reaction to solicitation than an older one. How do you manage this in your system?
The system, this is we were fortunate because the system has to be, the physical system has to be reset every 6 months or 12 months.
So you train every 6 months?
No, because when you reset it, I mean, 6 months are managed by the lifetime of the network with respect to the consumption of the cable. 6 months are managed. We are within. So, I mean, when you do industrial machine learning, you have to keep benefits from the real problem, the constraints coming from your problem. In this situation, the constraint was that the physical system is reset every 6 months. So the network starts again doing the good job when you reset the system. Okay. And it keeps doing it until the 6th month.
Any other questions?
In italiano è un problema?
No, assolutamente.
Ok. Solo una curiosità. Invece che analizzare le vibrazioni del cavo, avete pensato anche semplicemente al contatto metallico fra il capo e il moschettore del lavoratore, nel senso per rilevare la presenza?
Sì.
Era possibile oppure non era applicabile come soluzione?
The question for non-Italian is that if we thought about not registering the acceleration of the cable, but instead measuring a current passing within the cable with respect to the ground with some kind of resistance or so. And the answer is that yes, we thought about it, but it is not possible for the regulations the system must fulfill, which I mentioned before. I mean, you are not allowed to make any so weak current. And then you have a problem about the fact that the resistance is different with respect to the dimension of the system, and so you have to make a lot of on the field setting when you install the system. You keep in mind that this kind of system is installed by absolutely non-trained personnel. I mean, they just put the thing within the cable, near the cable, switch it on, it connects automatically to the internet, it gets the neural network, and they start doing the job. They just took working to test it, and they are done. They are specialized in installing the cable, not the electronics of the neural network. Thanks.
If I can ask you something. So first thing, it's again a great job. I mean, it seems like something very nice and complicated. So my two questions are about simplification. The first one is perhaps too simple to answer. So you have a phone on their, like in their pockets. You know where the cable is positioned. So with some degree of accuracy, you can know with a GPS that the guy is in the middle of the cable. So Anders, like this could have been an approach, or what is the problem of this? And the second thing is, since you have decided manually which feature you wanted to use, and since you use an activation function like, was it 10H or Sigmoid?
Sigmoid.
Yeah. And since you're using a single layer network, haven't you tried something simpler like SVM with radial basis function, kernel, or something like this that has proven to be, with the pre-selected functions in the past, very accurate and very interesting?
Actually, we had for every algorithm we had to test in this scenario. We had to test it both on the data and on the Cortex M4 processor. So we had to build the algorithm to write down the algorithm in C code from scratch and build it for an ARM processor. So once we were glad with this algorithm, we stopped it. And the answer to the first question is a domain kind answer, because one of the problems maybe I didn't mention it about is that if the operator tells that he is attached to the rock, but he is lying about this information, there are legal consequences. And so you have to be sure the system is detecting for sure that what the operator said about his compliance with the normatives was really true.
Yeah, but you can attach a GPS to the cable. I guess that's. I mean, the application could be always on. Like it doesn't need to open it.
No, yes, but the GPS on the cable doesn't tell you if the cable is attached to the cable, to the second cable. There are two cables.
Are you measuring the one that the person is attached to the big one?
No, you measure the big one.
So the one that
is fixed on the roof.
Is the one.
Yes, the accelerometer is not on the. Yes.
No, I thought it was on the other one. Because like.
No, maybe this is an important
I tried
point.
to look up on the web and like. It's
no, this is an important point of my presentation, because if this is not clear, you can see it here. The man is there and the accelerometer is there.
Yeah.
So, few last questions? No? Okay. So, thank you, Stefano, for the
Thank you
great
very
talk.
much.